okay? So you have plateaus here and here. So as you can see, the axis down here says heat is added. So heat and temperature. And I've said some things in first period over the course of a couple of days in your guys' class. Forgive me if I repeat myself. Let me know if I don't explain something well enough to you. So the heat and the temperature, which are the two axes here, because they're denoted separately, can you just say temperature and heat are the same thing? No, because they are denoted separately. If they were the same thing, we couldn't label those as independent variables and dependent variables. So what you see is as heat is added, this substance changes phase. But does it always increase in temperature during that phase change? No. And so there's only certain times when it does increase temperature. And that's the point where we'll look at starting point negative 40 to 0. What happens at 0? It goes from solid to liquid, and it starts the phase change at 0, but it finishes the phase change at 0 as well. So the temperature never changed, but the phase of matter changed. So basically, what did we go from? How does a solid look? Very compact and tight, right? So like this, and then we go to liquid, which is kind of like this, right? So what really happened? They separated, right? But why does it need heat to separate?
Because it gives it energy to overcome the intermolecular forces.
Beautiful. Okay, so these have strong IMFs. Remember IMFs? Intermolecular forces, the forces of attraction between molecules. Pretty strong. That's why they stay close together in solid form. And as we add heat, we're going to call it PE, potential. It's not actually potential energy, but it gives a sense of potential energy. It actually changes the particles' relationship to each other. So as they start to spread out, it's simply because the heat gave it enough energy to do that. So during this phase change, and this is like the most important part of understanding the heat diagrams. You should write this down. During phase change, the heat energy is used to simply overcome IMFs. That's what the heat energy is used for. And so since all that heat energy is used to overcome the intermolecular forces, it does cause a change in potential energy, not a change in kinetic energy. And that change in potential energy really has nothing to do with the temperature of the substance. So if there is a change of potential energy, which is the relationship or the spacing there, it doesn't influence the temperature, and that's why the temperature stays constant. But what happens as soon as I get here? What do the particles then start to do? They start to, why are they speeding up? You're adding more heat. So the heat's increasing, which makes them speed up. Well, speeding up is a way of saying increased kinetic energy. So motion, right? Kinetic energy relates to energy of motion. So if I'm adding heat, they're getting excited, they're moving around faster. Moving around faster means kinetic energy is increasing. So they're increasing kinetic energy. So basically they're just moving faster, right? Have they started a phase change yet? Not yet, but once they get to this particular temperature, it's different for every substance. Once it gets to 100 degrees at that high kinetic energy, then it's like, I can't be a liquid anymore. I'm going to have to separate even further and then boil and turn to gas. And then yet it goes, again, undergoes another temperature change. So that's why we can melt something and continue to heat the water, and then we can evaporate it. It doesn't phase change at the same temperature for both those phases. So that's why we use these heat diagrams for quite a bit. What do you notice is different between this one and the one we talked about more intensely yesterday? This is, okay, so this is called a heat curve. But it's a staircase, right? So, and there's also axes that are labeled differently. Carrie, what are you going to say?
It doesn't account for pressure.
Right, so we're assuming pressure is constant because there's no indication of pressure changing, correct? On the other one, we had that temperature, the temperature was on the x-axis and pressure was on the y. So we can see a lot of dynamic variables, changing pressure, changing temperature, and what happens? Oh, the phase changes based on different conditions. So let's look through this on the back of this. Can you guys go ahead and take 5 or less? and do where it says section 2. Some of you guys maybe already attempted parts of it and appreciate it. So if you've already finished section 2, go ahead and go back up to section 1.
Yeah. Wait, you mean section 2?
Yeah.
I'm thinking about
Yeah, section 2.
Between the pep rally, you guys are like a half class behind, and I can't remember what our function is called. Should we do the graph? Yeah, you're not going to do something probably very well. Okay. So, I'm waiting for this to go off. Okay. So, what is the phase of the substance at point A? Everybody. Solid. Good. What about F? Gas. Okay. So you know how to read the curve without labels. Or this curve. I say curve with quotation marks. Staircase. Look at D. I mean, sorry, at 5. What's happening from D to E? Tell me the phase change that's associated with that. Vaporization is a fancy word for it. You could say boiling, but vaporization is a little bit more sophisticated. How about E to D, number 7? Say again? Condensing or condensation. That works? Okay. I'm going from B to C now. What phase change is that? Melting. Okay, and then what about from B to C was melting, so that's what C to B? Freezing. So you know your phase changes. What's not represented here as a phase change?
Sublimation.
Sublimation. What's the opposite of sublimation? Deposition. Okay, so the opposite. So what is sublimation? Going straight from solid to gas, and the opposite of that is gas to solid. So that's not here because this is the way this curve works. Okay, so at what point? Actually, lies. What is the freezing point of the substance? 290. What's the melting point of the substance? 290, same temperature, right? We did talk about this because it doesn't matter. It is the same point. It just depends on which way you're looking for it. Solid to liquid or liquid to solid. 290 is the answer. What about boiling point, number 14? 310. What's the condensation point? 310. Same thing. It just depends on which perspective you take. Any other questions on this, guys? Have you guys ever seen a curve like this? No? Nah. I mean, but like, have you ever seen a heat curve? Cool curve? Phase diagram? What was that like? That was what we did yesterday. I thought you guys did something like that in 8th grade, but who knows? Yeah.
How would you get to 15?
Describe an actual. You put some ice on a hot plate, crank it up, see how the phases change. Eventually, it'll start to change, or maybe not ice, since ice definitely won't melt at 290. But some other substance, some solid, you heat up on a hot plate, and it'll go through liquid and then gas. Unless it sublimes really fast, then you don't really have a chance to see it. Or having, some solid out in the sun and it starts to warm up. Anything that will cause them to warm up. All right, so let's do one of those on the number 1. So which one do you guys want to do? 1, 2, 3, or 4? No, I'm doing 1. I'm here 2. Okay. I said which one you want to do? Okay, number 2 on the section 1. Graph temperature versus time. Okay. How do I write that? Where does temperature go? On the Y. And time goes on the X. Okay. Nitrogen. So as it goes from gas to liquid, so we're not going to start low. We're going to start high. You with me, Nick?
Yes.
Okay. So we're going to start high. We're going to start on the highest part of our graph, and it's going straight from gas to liquid, right? So how do I start this? A flat line or a slant? A slant line up. Okay, so it's condensing eventually, and then straight, and then. Okay, so do I go to solid? No. It doesn't say to go to solid, right? It just says gas to liquid. Okay, so I'm going to put a little G here, and an L here, and call that a day. Okay? This says that it condenses at -210 degrees Celsius. Where does that go? So tell me when to stop.
Stop.
Okay. So here, is negative 210. Negative 210 is where it condenses. Isn't that crazy? So, like, what would be a good melting point for that? Or freezing point for this? If I had to continue.
Negative 400.
Say again?
Negative 400.
Negative, okay, it should be lower. Negative 400 would be where it would freeze. It's a really low freezing point. That's a really low melting or boiling point or condensation point as well. So sometimes it'll just say graph one or two phases, not all three of us at that point in time. Okay, cool. So that's a cool curve. Why? Because we are going from gas to liquid. Which of these has higher kinetic energy? The gas, because it's moving around much more rapidly. So this has a high kinetic energy. Okay, the liquid has a lower kinetic energy. How in the world do you decrease in kinetic energy? But you cool it. So this gas has to be cooled. But what is the gas doing itself?
Please, for any interruption, any students who have not completed their AP pre-admin session, please report to the cafeteria at this time. Thank you.
Ooh. Okay, I'm videoing for you. Bye. If you are O through Z and you're taking an AP exam, or AP exam, not AP Chem exam, AP exam, then you're good. Bye. All right, Nick, tell me, how do I get a gas to lower its kinetic energy?
Okay, so first you have to cool the gas. You have to cool the gas because when you apply heat, it gives you kinetic energy, so it can counteract the intermolecular forces. So if
Okay.
you cool them, then they'll come together because the force is stronger.
How do I cool something?
You
Blow on it.
How? Okay, so the gas has to do what with its energy? Okay, it's either you either take in energy as a particle or you release it. Release it. Okay, so I asked it really broadly. I wanted to see if you guys could pick it up there. Okay, so this is releasing energy. As you go from gas to liquid, it is releasing energy, and that allows it to condense, which allows it to do whatever. So the term releasing energy, would you associate that with endothermic or exothermic? Exothermic. So write that process down as exo. The whole it's not like a reaction that's exothermic, it's a process because it's just liquid gas going to liquid. But that means that gases release energy as they form liquid. That means liquids release energy when they form solid. So that means during freezing, the process of ice freezing, it's releasing heat. While it's freezing, it's releasing heat. That's kind of like an oxymoron, right? So, an onomatopoeia? No, oxymoron. Ow! Okay. That's an onomatopoeia. English. Okay. So basically, that's it for states of matter. I will show you a quick video later of plasma if I can. But we're going to talk about gases really exclusively now because those are the most fun ones. Those are the ones you can do a lot with. And we'll actually do some labs with them tomorrow, some like hands-on. Okay? So if you're not going to be here tomorrow, I'm doing your notes today so that you're not out of luck here, okay? So go ahead and write down your variables of gases. I'm giving you guys a couple minutes here because this is a lot of information. Write this down. Yeah.
Cooling for epidemic and heating for
Hey, isn't plasma like fire or lightning or whatever?
Lightning can cause plasma to form. It's basically electrified gas. Which is why I like it.
I think there was like a fifth thing called Einstein or something. Like, what's that? I've heard about it a lot.
Something very, very, very
We discussed it because
Sure. Let me
I
actually
have absolutely
research
no
it
idea
more.
what.
Guys, I'm not talking to any of you till you write this down. You guys like to get me real distracted, and then we get behind. No. Let's go. Thank you. Fourth grade. Nonsense.
Either that or her office.
Is on pressure?
Yes, yeah.
What causes pressure?
gas particles collide with the other side of the container.
Beautiful. Nice, Miss Harris.
Miss Harris.
I'm gonna scroll down for you in a second. Out here pulling a Megan.
You're gonna have to do it a little bit more.
Whoa, whoa. I was at 10.
Pull that up on my website. I'll go back to it. I'll go back to that slide in a second. So it's under Unit 5 docs. Whenever you pull it up, you do have to say allow, sorry, this is say later, and then allow. Later just means you're not installing Adobe. It will already, okay, sorry, I installed Adobe. It should immediately, I'll go back to that slide in just a second. So there's two pieces to this, guys. So the whole idea is that gases are invisible. We can't see them. So the simulation gives you some perspective on how pressure, temperature, volume, and number of moles all come together. So I'm going to go back to that slide for you in a second. But when you get to the PhET link, right underneath the PhET link is a little worksheet. And the worksheet is really valuable to see on one person's computer and the simulation on another. So you're going to have a separate piece of paper out because you will be trying this in probably not today because we not do this whole thing, but we'll be close. So those two things you're pulling up is what and what? The simulation and the little worksheet questions that go along with it. So the first couple things you guys see are drawings or boxes. You see that? Are you in the right thing? So the first thing you see is understanding gas laws and understanding how the variables relate. This right here might be something you save and do after you see the simulation for a little while, because then you'll understand what it's looking for. Like, how do you draw a particle moving fast? How do you draw it moving slow? So you might just take a peek at this and go, I think I can draw that afterwards. But if you already have a good idea of what you can do that now. I'm expecting you at least halfway through. And you'll know some of the questions say, like, put in hundreds of heavy species, allow the pressure to stabilize, record. So do follow those very specifically. If you need any help, ask away. I'm coming around. Otherwise, get started. Yeah, I'm going to go back now.
Oh my God.
Oh, sorry. Is that good? Can you bring him up? See, many of you just trying to blow the lid off, that's totally fine, but then actually try the questions after that.
I didn't think that personally everyone could have done that. Is it 1 through 16? Just in case. Be back. Take your hat off, Chris. Certain people are requested for registration, I think. They act the way you think they're going to act. You know a lot about gases already, just inherently with everyday life stuff you deal with. So from here on, go ahead and halfway close your computer. We're going to kind of apply this in a more mathematical sense. So we'll get to these laws in a second. All right, halfway close your computer, so I know you're with me. At least halfway close it. If you all the way close it, just don't forget to log out later. Okay, box of air. Got your box of air. All right, so we got the box of air. This is a certain volume right now. Let's call it 1 liter, okay? And let's call it 1 atmosphere. And there's 1 mole in here, okay? What happens if I expand my volume? What also changes? What happens to pressure? Why does it decrease? Okay, so there's more space for the particles to move around. There's more space, I heard, Max.
Because it takes longer for the particles to collide with the walls of the container.
Okay, so if I expand my volume from 1 liter to 2 liters, they have more space to play. What is the premise of pressure? Definition, you just write it down.
How it bends off the container walls.
Collide. If you're going to talk about pressure, you have to use the word collision. So there's less, simply, more places to play, less collision to the container wall, right? Because the container is bigger. So what happens to pressure? So give me a number. Let's say I took 1 liter to 2 liters. I'll take 1 atmosphere to 0.5 atmospheres. Great. Okay, so we can see that pressure relationship just off the bat. What about if I have a container and I must maintain the pressure? The pressure has to remain the same. So I got my container, right? What if I heat up my gases? What are they going to do? Okay, why are they moving faster? Because temperature is average kinetic energy, right? So increasing kinetic energy means they move faster, and that's simply because of the temperature rising. Okay, so if they're moving faster, what are they doing with their container walls?
They're hitting them more.
They're hitting it more often. What is going to happen to pressure?
It'll
And I don't want the pressure to increase, so what do I do to it?
make the walls bigger.
So you increase the volume to combat the whole pressure, because if I want pressure to remain constant and the temperature is making the collisions happen more frequently, I can't have that. So I've got to increase the volume to keep my pressure constant. So you guys just said, let's say I had 1 liter and I had 100 Kelvin. I raised the temperature to 200 Kelvin. What did I do to my gas? Because I said I wanted the pressure constant. You made it bigger, so give me a number. 2 liters. Okay, so what do you notice that's different between these two scenarios? Go for it, Max.
One's inverse and one's like this, like
What's the word for that?
Indirect.
One's an indirect relationship and one's a direct relationship. So that's what we're basically going to be looking at from here on out. Because what you saw here was volume and pressure. Were they increased the same way, or do they inverse or oppositely increase or decrease? Opposite, right? As volume went up, pressure went down, okay? But as volume went up over here, as temperature went up, the volume went up, so they were both increasing. So we're going to actually assign people's names to this. Do you remember like Boyle's Law, Charles's Law, Dalton's Law, Gay-Lussac's, Graham's Law? These are all on your reading guide, so that's why I want you to keep your reading guides until I'm ready for it. Because you'll notice there are a couple things that are nice to reflect back on, because you may have written it really nicely, and then you can go back and kind of elaborate from there. So here's what we're going to do. We're going to identify the 2 variables that are changing in a given law, and then we assume the rest of them are constant, and then we'll write the formula for that. So take detailed notes with me, okay? So Avogadro's law. Avogadro actually took substances, and he counted the molecules, hence Avogadro's number, right? And upon counting those molecules, he then said, okay, well, this many gas particles gives me 1 liter. This many gas particles gives me 2 liters. This many gas particles give me 3 liters. So there were these ratios that he started to kind of achieve, which gave us Avogadro's number. So he compares N and V. N means what? Number of moles, and that's what you guys just wrote down. And so we'll assume that these will change, but we'll have constant. What other variables are not changing? Pressure. What's the other variable? Temperature. So you guys just write down your notes of the variables. When I say variable, I'm looking for amount, volume, temperature, pressure. If I say unit, what's a unit of temperature?
Kelvin.
Yeah, you cannot use Celsius, you must use Kelvin. What's a unit for pressure? Kilopascals, there's 2 more. Atmospheres and millimeters of mercury, right? And so there's equivalencies that connect all of those. Volume can come in what varieties? Liters or milliliters, but N must come in moles. Okay, so you got your box of air, right? It's at a given volume. Pump some more air in there, okay? So pump some more air in there. You want the pressure to remain the same, okay? Because it says at constant pressure. What do I have to do to this box to expand it, right? Because what's going to happen as soon as I put more gas in there?
It's gonna go flying.
They're going to start colliding with the container wall. That pressure goes way up. I've totally obliterated my problem, right? So we're going to want our pressure to stay constant. So we need to watch the volume. Increase it. So we write let's write this whole thing for me and I'll explain it. N1 over V1 equals N2 over V2. This is Avogadro's law. He says that as you increase moles of gas, you're going to have to increase the volume to maintain your constant pressure and temperature. So that's what we're assuming those are staying constant, whereas we're increasing both of these. So is this a direct or indirect relationship? Because they both go the same direction. Increase, increase. So very commonsensical. Your box of air is your best friend for a little while, okay? So Boyle's law, similar situation, but we're now going to be using not moles. We'll say pressure and volume are what's inside of that formula, that comparison. So what's remaining constant? And moles, right? That's an in. So if we're remaining constant moles and constant temperature, let's talk about our volume and pressure changes. This is kind of what we just did a second ago over here. I have a box of air. I increase the pressure. Okay, squeeze it. So what happens to your volume? It decreased. So you said increasing pressure causes decrease in volume, right? Because that's you're compressing your air. And that allows your temperature and your number of moles to also remain constant, just because we never change them. So there's a law for this one. Oh, actually, tell me this first. Indirect or direct? Okay. It's an indirect relationship. So notice how I wrote this one as a division. When it's a direct relationship, we write it as a division. So how do you think, I'm going to write this one as a multiplication, right? So P1V1 equals P2V2. So the reason I'm writing ones and twos are because many times in a situation I might be like, okay guys, I got a balloon. I'm on the top of Mount Everest. My balloon is a liter in volume. Walking down Mount Everest, what happens to my pressure? It increases. What size is my balloon? Why? The atmosphere around it will compress it, right? So I can tell you in one story 4 variables. I can say I'm on top of Mount Rushmore, or on top of, the world, and I can say, okay, I'm at 0.5 atmospheres, and my balloon is 1 liter. Okay, and as I go down the mountain, what happens to my pressure? Let's call it 1 atmosphere, right? And I might say, what is my volume?
0.5.
So you think, right? Well, we have mathematical equation now to show out our work for that, because you know me, and those units, they will be the death of us all. Okay, so the next one. So we can start to see how these are scenario based because I'm labeling them 1 and 2. Scenario 1, scenario 2. Okay, so I like to say Charles went to Virginia Tech. What 2 variables is that? V and T, thank you. So when I say Virginia Tech, you should be thinking volume and temperature. So at constant what?
Pressure.
Yes, pressure and moles. So are you guys seeing where we're getting the constants from? Your 4 variables we wrote down 10 minutes ago? Yes? I got Joe saying yes?
Yeah.
Perfect. Okay. Are you figuring out where we're getting the constants from? Because we have 4 variables, and if 2 of them are changing, the other 2 are staying constant. Okay, so my box of air. You got your box, about 1 liter of your box. Speed those babies up. So you're heating it up, right? Speeding them up. What are they doing? Bouncing around like crazy, right? So they're colliding, and what are they doing?
They're colliding on
They have absorbed that kinetic energy. That's why they're moving so fast, right? But they're hitting the sides of the container. Oh no, the pressure is what? We don't want the pressure to increase because if we say it remains constant, so we increase the volume to stop the collisions from occurring so frequently with the container wall. So you just said increasing temperature causes increase in volume to maintain those constant pressure and number of moles variables. So direct or indirect?
direct. So how do I write it? As a division or as a multiplication? Division. Who's going to go on top? Volume over temperature. V1 over T1 equals V2 over T2. Okay, so we got ABC. Who's first? Avogadro, and then Boyles, and then Charles's. ABC. Yeah, so we'll go over Dalton, which is D, later. He's not today. But we will go over Gay-Lussac's. Can I go forward? Okay, so, ooh, I didn't erase this. Well, I'm going to show you that now, aren't I? Don't look. Don't look, I'm going to write it. I like to go slower with you so that I know you're getting it. Zach just dropped the bus. Yeah, thanks. All right, so those never works for me. Never works. Thank you. Okay, so Gay-Lussac's law, right? So what's your variables that we have to compare? Volume. Say again?
Volume and N.
We did that. That's Avogadro's.
Oh, yeah.
Temperature and pressure. Pressure and temperature change at constant what? Constant V and N. Okay. So I have my pressure. I got my little guy in the container. Now this container is a steel drum. I can't change the volume. I put some fire underneath it. It's heating it up. What happens to the particles? They start moving around, and they boom collide with the container wall, and then they collide with the container wall. Okay, it could explode because the volume can't change. But before it exploded, the pressure increased until the point in which it explodes. Okay, so increasing temperature caused increase in pressure because of the collision aspect of that. So direct or indirect? It's direct, and we're going to write our equation how? P1 over T1 equals. Beautiful. Okay, now, that's everybody's laws for now. These are all the pressure, volume, temperature, mole relationship ones. What we can do is we can actually combine Boyle's, Charles's, and Gay-Lussac's, actually. Gay-Lussac's, and we'll deal with later. And we can put them all in one. So you think about it and tell me, where is the P, T, and V going to go? There's no products or reactants. This is our pressure, temperature, and volume. So how did Boyle's law describe its stuff? That's our ideal gas law. We'll get there later. Look at Boyle's law. What's Boyle's law? P1 times V1 equals P2 times V2. Okay, what's Charles's law? So what do I do here? Over T1, and this one over T2, okay? And what's Gay-Lussac's law? It's already there, right? So it's all combined already. So what you can do is sometimes, because you guys will memorize these, what a lot of people like to do is they just memorize the combined gas law, and they're like, oh, constant volume, ignore volume. I use Gay-Lussac's law. Oh, constant pressure, ignore pressure. I have Charles's law. Oh, constant temperature, got that. And whose law is that? Boyle's law. Do you see how the combined gas law, if you cover up two variables that are constant, it actually shows you somebody else's law? So it's nice because it's kind of combined. So we're going to use this and talk about, I don't believe I've passed this out yet, right? No papers for me today, right? All right, so let's talk about how do we look at scenarios and decipher the problem. I may not have passed back enough, but we'll try. See if that will help. Make sure you grab one. So guys, we're going to go ahead and do question 1. You should not be distracted by your phones or I can take that precious, precious bean from you. And I will clicker up. Clicker. Okay. So we'll talk about pressure actually more in depth tomorrow, but I think you got the gist of it. Pressure is caused by atmospheric pressure and collisions with the container wall.
We'll talk about barometers tomorrow. You probably want to have a couple of questions under your belt before you leave me today. So, do you see this question on that worksheet?
Yes.
Where's it at? Number one. Okay. So here's what I expect to see, and this is setting you up for success if you follow my process. It's all about the process. Go ahead and look. Do you see the answers on the end of the sheet? Yeah. Okay. So you're welcome. Those answers are there for your checking yourself, patting yourself on the back. I hope that you guys pat yourself on the back many times tonight. Jump in. We're solving number one. Let's go. Okay. This is number one. So this is under the Boyle's Law section. Now I did partition it. I said this is Boyle's Law, this is Charles's Law, this is Gay-Lussac's. But in the future I won't be telling you that. Your job is to decipher which law to use. So the first thing we'll do is we'll read it and write down our givens. Okay, so let's read it and write down our givens. What's the first thing you see? 700 mmHg. mmHg is a unit of, which are the four variables? Yes, pressure. So write P equals 700 millimeters of mercury. Okay, of a sample of hydrogen has a volume of 500 milliliters. You are writing this down with me. All right, so this already tells me what the variable is. What is it? Volume of 500 milliliters. Okay, so that's scenario one. You see it says a sample has this pressure and this volume. Do you see that those are given together? In one scenario, I'm going to label both of those 1 because they're given together in one scenario. Okay? And then the next scenario says, whoa, if the pressure is decreased to this, so what is this? P2, that's my second pressure given to me in a separate scenario, 538 millimeters of mercury. What will the new volume be? What's my question? V2. The volume that's associated with this pressure. So, one second. When you read the question, pause and go, which variable is this? Take it down, label it. The second scenario will kind of give you a new information. It's pretty obvious. It's usually first sentence and second sentence, but then they'll start to blend the variables. So, step 1, given. Step 2, ID the law. Whose law has P and V and P and V? Boyle's law. So all of this information here goes into Boyle's law. So then you reference your brain and you're like, I know Boyle's law. What is it? You guys with me? Okay. You're supposed to say it. Yes. Yes. Okay, so ID the law that should be used. So we see the variables. You find the one with those variables in it, that's the one you use. Third, isolate the question variable. Okay, so what are we looking for?
V2.
V2. So think mathematically, how do I isolate V2 by itself? Thank you. No, I'm not filling anything out. I'm simply isolating this variable. Yes. On both sides, right? So I'm dividing by P2. Keep it cracked, please. Keep it cracked for the rest of them. I'm dividing by P2 on both sides. Why am I dividing by P2 on both sides? Because you want to cancel P2 on the side and you want to get what? Don't shut my door. V2 by itself. So this cancels, right? So then what is V2 essentially just equivalent to? P1 times V1 over P2. Algebra, right? No stoichiometry for a little while. But it's not going away. It's coming back. So if you didn't learn it the first time, you best study that over the spring break because we'll start at day 1 on Monday. So this process here is just algebra using equations. So
good afternoon, staff and students. Teachers,
Me too.
at this time, if you could please read an email that Mr. Smith just sent entitled "Announcement." Again, good afternoon, staff and students. Teachers, if you could please read an email that Mr. Smith just sent entitled "Announcement." Thank you.
Okay. So plugging this in so I can have you guys calculate. Nick, what's the next variable I'll plug in?
The next variable you plug in, which would be V1, which is 500 milliliters.
Okay. And I'm plugging my units in and everything else.
Get through the bottom one.
And then what's my bottom one?
P2, which is 538 millimeters of mercury.
Mercury. Good. Jonathan, what units cancel? Millimeters of mercury and millimeters of mercury. If my pressure units were not in the same unit, I would not be able to cancel them. I would need to convert that first. But because I am, I'm good. Milliliters remain. Calculate.
600 what? 650.55, and that's milliliters, right? Okay, so then I go back and I say, how many sig figs should I have here? 3, so 700 is 3, 500 is actually 3, I have to put 0 by accident. 538 is 3, so round this to 651 milliliters. That is how you solve a gas law problem. First step was what? Given. Second step was, how do you ID the law?
You just look at what variables.
Look at what variables you have, which we had PV and P and V. That stood out, smacked us in the face as who? Boyle's law. And then? Isolate the variable. I think it's so much easier to isolate the variable in the variable sense here before you start plugging in, because I know you guys and I know me. We got better fingers. We'll start plugging something in wrong, and then it's really hard to find your mistake after that. And then isolate, plug, 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 cancel, 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 solve. Okay? You guys have 1 through 16. 1 through 16. You guys have 7 minutes right now. Do not pack up. Please proceed to the next example. Yes, you can log off computers, but do not pack up yet. I need you guys to work through a couple of those examples without me.